Because my answer is no.
It could be a billion, right?
Could be whatever I want it to be out of. I'm not having this conversation with you right now.
Why is assignment released yesterday night? Yesterday, the TA did it so. Why did TA release it so late?
Okay, good morning, everybody. So just to begin, there is a test next Wednesday in class. So originally it was scheduled for the Monday, but I was asked to move it, so it got moved to the Wednesday. So it is in class, it is written, so you need to bring a pen or a pencil. There is a sample test online. If I remember, I'll post additional older tests later today or later this week. Generally, the first test is pretty well done by students in the course. The material covers up to the previous lecture, so it doesn't include today's lecture. I'll post an announcement on OnQ explaining exactly what will be covered on the test. All right. Okay, so to remind you what we were talking about from the previous lecture. So we were working with lists, and we were doing some recursion with lists. And so the problem that we were looking at the end of the last class was you're playing this not particularly fun game, but we're trying to solve this problem where you have a board where the board is represented as a list. You start at the left-hand side of the list and you try to make it to the right-hand side of the list. The numbers on each square indicate how many squares you're allowed to move left or right. And you're not allowed to fall off the ends of the board. So for example, to solve this particular board, starting at the left, we move 2 squares to the right, and we land on the 4. We're now allowed to move 4 squares in either direction, but you can't move left because that would take you off the end of the board. So we move to the 1, right? When you get to the 1, you can go either direction. I'm going to arbitrarily choose to go to the 6, right? From the 6, I can't go right, so I have to go left, and so on and so on, and so forth, right? So you end up at the end of the board in this case. There's another solution on this board. You can go left at the 1 instead. When we get to the 2, I can go to the other 2. Notice at this point here, I can go back to the other 2, but I don't want to do that because I'm just going to end up going around in circles. So we keep on going, and eventually you end up at the 0 again. Right? If you find, in this particular version of of the game, you can end up going around in circles. In this case, you can end up going around and around and around if you alternately move left and right, starting at this 2. Right? Go left, then go back to the right, and go left and go back to the right, and so on and so on and so forth. So you want to avoid moving around in cycles because they don't actually help you find a solution. Right? If you have a cycle on a board, you can easily make a board where no solution exists. So here we're stuck going around and around and around with no solution. Right? And of course, and on this board here, no matter what you do, you end up in a cycle of some kind. You end up on the 1 eventually, and that forces you into a cycle. And even without cycles, you can end up with a board that has no solution. So here, starting at the 1, you go to the 100, and now you can't move in either direction. All right, so unlike the previous version of the problem that we looked at, this version of the problem does not really look like it gets smaller, at least not there's no obvious way that, that the problem gets smaller, right? So remember in Jump It, we always move to the right. And so every time you take a step to the right, you can ignore the board to the left. And so the board gets smaller and smaller and smaller. Eventually, you end up with a board of size 1. And you end up with being able to compute the cost for the board. If you want to solve this particular problem with recursion, remember that in recursion, if you want to guarantee that your recursive algorithm ends at some point, the size of the problem that you solve at every step has to get smaller and smaller and smaller. So the question is does this version of the problem actually get smaller at every step? And the answer is, in fact, yes, right? And so in this particular version of the problem, every time you step on a square, you don't want to end up back on that square again. So in other words, you're going to reject solutions that put you back on a square that you've already been on before. And what that means is that you can, the problem gets smaller by 1 square every time. So that looks like, it looks like we can then try a recursive approach to solve this problem. Of course, in order to solve the problem using recursion, we need some way to indicate that we've been on a square before. So we're going to have to do something to the board or remember some extra piece of information regarding the board. Okay, so how do we solve this recursively? So usually when you start or when you implement a recursive method, it's probably more common that you define the base cases first. I'm going to do the opposite in this case because it's a little bit easier to figure out the recursive cases. So to recursively solve the problem, so we're on a square, and we want to know from this square, can I get to the end square of the board? So can I get to the right-hand side of the board? Right? You have to remember that the method that you're writing is the method that solves can you get to the end of the board from a given square. Right? So you land on a square. It's got some number on it. That number tells you how many steps you can move left or right. So if you can move left, so if the number is small enough that you can actually move to the left without falling off the board, right? You want to ask the question, so can I solve the rest of the board after I move left? Now remember, you have 2 choices at every step. You can also go to the right. So if you can go to the right, you want to ask the question, can we solve the rest of the board if we move to the right? And so once you figured out that these are your recursive cases, it becomes, you can immediately write down the code that actually performs the recursive steps, right? So first of all, you start out with your method. So here, I'm calling the method is solvable, right? So this is solvable returns true if that board can be solved starting on that square there, right? So the first time you call this method, you're going to pass in 0 and the original board. Okay, so the recursive cases, the base cases are going to go here, but the recursive cases are easy to implement, right? You want to ask the question, can you move left or right? So the first thing you need to do is you need to figure out how many squares am I trying to move, right? And so the number of squares that you're trying to move is simply stored in the board, right? It's whatever square you're on, which is given by index. So you ask the board, what is the value stored at this index? Right? That's the number of squares you can move left or right. Now, we need to indicate somehow that we've been on the square at that index. We've already been on this square, and we don't want to come back to this square. So the way I'm going to do this is I'm going to change the board. Right? I'm going to set the current square to some negative value to indicate that we've been on this square before. Right? So remember, the board values are all positive. If I set it to a negative value, that's one way to indicate that we've been on this square before. Right? And we're going to use this in the base case to test whether or not we've landed on a square that we've already visited. Okay, now we want to know, can we move to the left? Right? So remember, you're at this index here. You want to move that many positions to the left. So if you simply compute index minus value, that gives you the index of the location after you move left. Right? This has to be a valid index. So in Java, it has to be greater than or equal to 0. Right? So if it's greater than or equal to 0, we simply try to solve the board by moving left. Right? How do you solve the board by moving left? Well, you just recursively call the method. So we call is solvable, we pass in the new index, and we pass in the modified board. Right? Remember, we changed the board up here. So the recursive version, so the recursive call calls the method with the board that indicates we're on the current square. Okay, so that, if we finish implementing is solvable, this will tell us yes or no. Is the board solvable by moving left? Right? And you want to do the same thing moving right. Right? So the index after moving to the right is simply index plus value. Right? That has to be a valid index on the board, so if it's less than the size of the board, we're going to try to solve the board by moving right. So we're going to write another line of code that basically looks like that. Right? So we ask, is the board solvable? Moving to that square there on the current board. Okay, so at this point we've determined, can you win by going left and can you win by going right? So if either one of those is true, we can simply return true. So return win left or win right. But remember, sorry, back here, I skipped something here. The contract or the documentation for the method says that this method does not change the board. Really what it means is it does not permanently modify the board. Right? And so whoever calls this method, they pass you the board, and then when the method finishes, they expect their board to be the same as what as when the method first started running. Right? Here we're changing the board. Right? We're setting one of the squares to so its value is -1. We have to remember to undo the change at the end of the method. Right? So here we put back the original value that the board had. Right? And so that produces the illusion that we never actually changed the board in the first place. Right? And I claim that that would be a sufficient recursive. These would be sufficient for the recursive cases for this method. Right? Now we're not done yet. We still need our base cases. Right? So every recursive method needs at least one base case. Right? The method stops when the base case is reached. So you have to ask yourself, what are the base cases for this particular problem? Right? So one of the base cases is that you've landed on a square before that you've seen already. Right? Now, we've marked the board with a -1 every time we step on a square. Right? If you land on a square that's marked with a -1, you know the board is not solvable, so you can simply return false in this case. For a method that returns true or false, you probably need another base case. We have one that returns false. You probably need a base case that returns true. Right? You know that you're done if you reach the last square on the board. Right? In which case the board is solvable. So there's your second base case. And those are easy to put into code too. Right? So when you land on a square, if the value of the square is less than 0, you know that you've entered a cycle, so you can return false. When you land on a square, if that's equal to the last square on the board, you know that you've solved the board, so you can simply return true. Right? And then the recursive cases from the previous slides can go in here, and away you go. And so there's the recursive solution for this particular problem, for this particular version of Jump It. Okay. I guess for most new programmers, this method looks strange. It looks like you only ever set the board once, right there, right? So it looks like you only ever step on one square. But what you have to remember is that the method is solvable calls itself here and here, right? So when it calls itself here, it's, oops, sorry, this got some typo. This is a cut and paste error. That should be board, not copy. Okay, so it looks like we're only setting one square of the board, but what you have to remember is that the method calls itself. So when it moves left, right, the recursive version of the method is going to set the square that it lands on after moving left to -1 as well, right? And when you move right, the recursive call to the method is going to set the next square that you land on to the right to -1 as well. After your recursive calls finish, right, so remember these recursive calls will keep on going until one of your two base cases are reached, right? So after your recursive cases finish, we can unset the value of the board. Remember, the recursive calls are going to unset the board values that they modify as well, right? So it turns out this one, the method looks like it's only setting the board once, but in fact, it sets it every time it calls itself. So this does in fact produce a correct solution for this problem. All right, any questions about that particular method? Yes? Back here. So the method promises not to change the original board, right? So if inside the method we're setting a square to -1, right, that changes the board, right? Imagine that you're using this method to solve a board, right? So you pass in your board to this method. If you don't unset the value here, right there, right, after the method is finished, the board is now modified. So the board that you passed to the method now changes, right? Which is probably whoever calling the method doesn't want that to happen, right? They want their original board back, right? If you're going to change the board, the caller has to pass in a copy of their board if they want their original board, right? Yeah, right? So we set before we recursively call, we set. After the recursion happens, we unset. Yeah. Okay, any other questions? All right, so one more set of problems and then we're done with recursion for this course. Okay, so imagine you have a list, it's full of numbers or things that can be sorted. Right? You would like to move the smallest element in that list to the front of the list, right? So this is pretty easy to do if you don't use recursion. You find the smallest element in the list, right? So you loop over the elements of the list, you find the smallest element, right? Or I guess more precisely, you find the smallest element in the list, and then you can swap the smallest element with the element at the front, right? Another way to do it would be to remove the element from the list and then insert it back at the front. It turns out that's computationally more expensive than swapping. But how do you do this using recursion? Right? Okay, so here's a picture showing how you could do this with recursion. So here's our original list. It contains the numbers of the digits 0 through 9. I want to move that 0 to the front of the list. Right? I don't care what happens to the rest of the elements, as long as we don't actually remove or change the values of the elements. Right? So in other words, I want to move the 0 to the front, and after we're done, I want to make sure that the numbers 0 through 9 are still in the list. Right? So how do you solve this recursively? So you say, well, let's ignore the first element in the list. Right? Can I move the smallest element to the front of the list shown in blue? Right? So in other words, can I move the smallest element to the front of the sublist shown in blue? Right? So let's assume that we can do this. Right? After you do this, the number 0 is at the front of the sublist. I don't know what the rest of the elements are, but I know for sure the number 0 is at the front. Right? Once I've accomplished that step there, it's now easy to move the smallest element in the entire list to the front. Right? I know the smallest element in the blue list is at the front of the blue list. The smallest element in the entire list is either the first element of the original list or the first element of the blue list. Right? So compare them. If the element in the blue list is smaller than the element at the front of the list, simply switch them. Right? So here we can just switch the 0 and the 8, right? And that moves the smallest element in the list to the front of the list. Right? So what you have to remember when you're implementing this recursively is that you're going to write a method that moves the smallest element in the list to the front of the list. So to move the smallest element in the sublist, I can just use recursion, pass in the sublist, and ask the recursive method to move the smallest element of the sublist to the front. Right. The recursive version of the method is going to move the smallest element from the 6 to the 1 to the front of that list. Right. It's going to recursively call itself, so it's going to move the smallest element from the 4 to the 1 to the front of that list, and so on and so on and so on until you get to the 1. Right? When we reach the 1, there's only one element in the list, so the smallest element is at the front of the list. So it does nothing. Right? And it returns. Right? Now, the recursive version of the method that ran with the 9 and the 1 compares the 9 and the 1. Right? Switches them, so now you have a 1 and a 9. Right? So now the 1 is the smallest element in the sublist of size 2. Right? That recursive method returns. And so now you have a 2, a 1, and a 9. So compare the 2 and the 1, switch them, and now you have the smallest element in the list of size 3. And so on, and so on, and so on, and so on, until you get back to this situation here. Right? So putting this into code is relatively straightforward. Right? So for the base case, if the size of the list is less than 2, so in other words, your list is empty, or there's only one element in the list, there's nothing to do. The smallest element is already at the front of the list. So you can simply return. Right? Otherwise, right, you want to do the first step in the picture here. Right? I want to move the smallest element in the sublist, not including the first element, to the front of the list. So that's the recursive call there. Right? To compute the sublist, you just use the sublist method. Right? So t sublist 1, t size, gives you back the sublist of t, not including its first element. So that performs this step here, these two steps here. Right? And so now all that's left is compare the first two elements of the list. Right? So the first element of the list is stored at index 0 of the list. Second element is stored at index 1. Compare them. So if second is less than first, switch the two elements. Right? So to swap the elements, or in this case to switch them, we can use set. Right? So I'm going to replace the element at index 0 with the second element in the list. I'm going to replace the element at index 1 with the first element in the list. And that method there will recursively move the smallest element in the list to the front of the list. Yeah?
Why do we get a sublist T but can't get the sublist from?
So this step here, right? There's your sublist shown in blue, right? The method min to front promises to move the smallest element of a list to the front of the list, right? So when I call it recursively, it's going to move the smallest element in the sublist to the front of the list. Oops, sorry. So when I make the first recursive call, when it's finished, that 0 will be sitting at the front of the sublist. Sure. So let's work with a smaller list, okay? So we're going to do a list of size 3. And so we'll put it in reverse order, so 2, 1, 0. Right, so there's t. Right? So the first recursive call calls the method passing in the sublist 1, 0, right? Now, remember, in the recursive call, that sublist is going to be called t again, right? So in the next recursive call, t is 1, 0. Right? This version of the method is still running, right? So its t is 2, 1, 0. It calls itself, right? So the way recursion works in most programming languages is that when you call a recursive method, you get a new version of the method. It's not the same version of the method that's running, right? So you get a new version of the method. In the new version of the method, t is 1, 0. This is the part they don't tell you in 121. They don't tell you the mechanics of recursion. So now t is 1, 0. right? It recursively calls itself, so with the sublist, right? So the next version of the method runs with a t that's only 0. That's the base case, so it returns, right? So now this method goes away, right? And we come back to here, right? Now we've got a 1 and a 0, so now we do the comparison. If first is less than second, we swap them. So now we do the swap, and now this method is done. Now the cute thing here is that we're using a sublist. So remember, when you use sublist, you get back the original part of the list. So when you swap them here, those also swap. All right. This is the reason this works in Java, is because we're using sublist. Sublist always gives you back part of the original list. Right? And so when you do the swap here, you produce the swap up here. This version of the method is now done, so it goes away. Right? Now we finished our first method. We compare the first two elements, right? Switch them to get the 0 and the 2 there. So that's how it works. Wait. Yeah, one of the big parts with recursion, the way it's normally taught, is that they normally don't tell you that every time you, when you call a method, it's a new version of the method that's running. It's not the original version of the method that runs. Yeah. All right. So what happens if I repeat this process? Right? So I call min to front with the original list, and that moves the 0 to the front of the list. Right? So what happens if I call it again? This time passing in the sublist. Right? So when I call it again, with using the sublist shown in blue, min to front is going to move the 1 to the front of the sublist. And so now you get 0 and 1. Right? Now what happens if you do it again? Again, passing in the sublist to min to front. Right? It's going to move the 2 to the front of the sublist to reduce 0, 1, 2. Right? And if you keep on going, right, eventually you'll sort the list. Right? That's exactly the selection sort algorithm that they hopefully told you in 121, right? So remember, the way selection sort works is you repeatedly find the smallest element in the unprocessed list and move it to the front, right? After you've moved the element to the front, the rest of your list is then processed again, right? So selection sort repeatedly finds the smallest element in the rest of the list, moving the element to the front of that list, right? And so selection sort using recursion, assuming you have min to front, you can implement in 3 lines of code. Right? So given a list T, we can selection sort the list by moving the smallest element to the front of the list, and then sorting the rest of the list. The rest of the list is just the sublist starting at index 1. Right? Here, it doesn't look like there's a base case, but in fact there is, right? So the base case here is if the size of the list is less than 2, do nothing, right? The other way to write that is if the size is greater than 1, run the recursion. And so there's selection sort in 3 lines of code. But you need min to front for this to work. Okay. So how fast is selection sort? So this is just to remind you about this complexity stuff that you might have learned in 121, right? There's only 2 steps in that selection sort algorithm, right? The first step is move the smallest element of the list to the front. Now, to move the smallest element of the list to the front, you have to find the smallest element, right? To find the smallest element in a list requires you look at all the elements in the list, right? So that step there has complexity big O of n, right? Then you recursively sort the rest of the list. So the rest of the list has n minus 1 elements in it, right? So the way to solve this is that you define this, you define a, I forget what this function is called. So T of n is the number of operations needed to selection sort a list of size n, right? And so this ends up producing a recurrence relation, right? How long does it take to sort a list of size n? Well, I need to sort a list of size n minus 1. So that's just T of n minus 1. Right? And then I need to move the smallest element to the front of the list, right? So remember, every time we're moving the smallest element to the front of the list, so there's big O of n time. If you solve this recurrence relation, which they would have taught you or will have teach you in one of your CISC math courses, when you solve that, you get big O of n squared. So selection sort is a big O of n squared. It's a little bit easier to see if they show you the iterative version of the method, right? But you can produce the same result. You can get the same computational complexity by analyzing the recurrence relation as well. Right? If you don't know how to do this or you've never seen it, don't worry about it. You will see it eventually in one of your CISC courses. Okay, so that wraps up recursion in this course. I normally don't ask you a test question about this. This is a course in object-oriented programming. It's not a course in recursion. So I normally don't ask you any questions involving recursion on a test. If you want to, though, you can always solve a test question using recursion if you like. Right? But mostly, this was to show you how to use sublist and how to use lists in general. Okay, so having said that, does anybody have any questions about using lists? All right. So if you're following the lecture slides in the order that they're listed on OnQ, I'm going to skip over the next two lectures. So on OnQ, the next two lectures are sets and maps. I'm going to jump over them, come back to them later in the course. So I'm going to jump ahead to lecture number 12. It's called classes. So we're finally going to get to the point where we make our own classes. Question? No, it will not. But I mean, you need to know how to use a list. So there's lots of examples of using lists in those slides. So it's worth reading them. But I promise not to ask you a recursion question. Okay, so we want to start making our own classes. So in other words, we want to start the actual object-oriented programming part of this course. So before we do that, I need to tell you about some basic terms related to object-oriented programming. So remember what a type is, right? So a type is a set of values and the operations that you can perform with those values, right? So the type int is the set of values for int. They range from integer min value to integer max value, right? Roughly minus 2 billion to 2 billion. What can I do with those values? Well, I can do arithmetic, right? I can do comparison, right? And you can do a few other things with them, right? So the type int is just the type that represents integers between some minimum and maximum value. The type string, what are the set of values for strings? So for a string can be empty, so there can be no characters in the string, right? And there's no upper limit on the number of characters in the string. So the set of values are any sequence of 0 or more characters. Right? What operations can you do with a string? Well, I can compare them with equals, right? I can get an element out of the string. I can ask, does the string contain a character, and so on and so on and so on and so forth. Right? So a type is a set of values and the operations that you can perform with those values. Right? What's a list? A list is a sequence of 0 or more elements of the same type. What can you do with a list? I can get an element. I can replace an element. I can get it sublist. I didn't show you this, but you can use equals with a list. So two lists are equal if they have the same number of elements and they contain equal elements in the same order. Right? So in other words, you compare the two lists element by element. If all the elements are equal, the two lists are equal. Right. Okay, so in Java, it's got primitive types. We know this already. Right? Java also has reference types. We also know this. Right? It turns out arrays in Java are considered to be reference types. Any other type beginning with an uppercase letter is also a reference type. Right? Where do reference types come from? They're just classes. Right? So a class is simply an implementation of a reference type. Right? In other words, it's the Java code that defines a reference type. In Java, classes are types. Right? So when you make a class, you get a new type. Yeah. How is what different? Oh yeah, so the string, so I'm going to get to this later in the lecture. So there are some classes in Java that are defined in a package called java.lang. Right? String is one of them. Math is another. System is another. Right? The classes defined in java.lang, you can use them without specifying the package name. So you don't have to import them. That's not true for other types. So anything in java.lang, you don't have to import. So when you say string, people mean java.lang.string. Okay, so classes are types. So when you create a class, you create your own type. Right? Not all of the reference types are classes. So later on in the course, you'll learn about interfaces. Those are also reference types. But classes are, in fact, types, right? They are the definition of user-defined types. Okay, so what is an object? So an object is just an instance of a class, right? The number 5 is an instance of an int, right? The string ABC is an instance of a string, right? The list containing the numbers 1, 2, 3 is an instance of a list, right? What is the purpose of the class? The class is used as a blueprint to generate objects, right? So when you want to use, when you want an array list, right, you use the array list class to produce an object of type array list. Okay, so what are references? References are just some identifier that lets that lets Java find a particular object in memory. So in many Java implementations, a reference is simply a memory address, right? We don't actually care how they're implemented, right? Just remember that a reference is not the object itself, rather it's a way to find the object in memory, right? So anything that's not primitive, any variable that's not primitive stores a reference, right? So T in this case stores a reference to an array list here, right? Remember, T itself is not the list itself, right? Stores a reference to the list. Okay, so this business with references might be easier to understand if you draw a picture of it. There's lots of ways that you can draw a picture of this sort of thing. So a lot of books will use boxes with arrows and things like that. I'm going to do it in a slightly different way. So I'm going to show you what's called a simple version of a memory diagram. Right? So on your computer, all data is stored in memory somewhere. Right? Exactly how computer memory works is a very complicated subject. An easy way to think about it, though, is that computer memory is just a giant array. Right? And so it's a one-dimensional array. Right? The indexes of your array, I'm going to call an address. So you can imagine that memory is indexed starting at 0, right? Address 0, then address 1, and then address 2, and so on and so on and so forth. Right? In our model of computer memory, we're going to store a value, a single value at every address. Right? So for our values, we can store things like numbers and references. So those numbers, true, false, and references. And that's all that we can solve. That's the only thing that we can store. Right? Over in our first column, we have a variable name. So if you've got a variable of some kind, we're going to remember the name of the variable. Right? The name of the variable name is stored in an address somewhere. Right? And the question is what's stored in this column over here. Right? So for a primitive type x, double x, right? Here our variable name is x. Right? It doesn't matter where you put these things in memory. I've just stuck them arbitrarily at 100, 101, and 102. Right? The numbers actually, this address, the numbers here aren't actually that important. Right? So for a variable x, if it's primitive type, the value that's stored in memory is the value of the primitive variable. Right? So the value in memory here is -1. Right? Here I've got two reference types, t and u, or two reference variables, t and u. So t is somewhere in memory, right? The value that it stores is a reference of some kind, right? So for our references, I'm just going to write down the memory address of the actual object. Right? So t refers to some array list object. That array list has to be somewhere in memory. I'm going to put it down somewhere. It doesn't matter where. Right? So I'm going to drop it down at address 700 here. So sitting here, there's an array list object. I don't know what's in the object. So I've just got this array list string object line here, right? We don't know what's inside the array list, so we don't know what it looks like in memory. But there's some stuff sitting here, and probably below it, right? So the value stored in T is the address of the object, right? So it stores the value 700A. The A indicates that it's an address and not the number 700. When you write U equals T, what does that mean in Java? Actually, what does it mean in Python? Because it means the exact same thing, right? When you write something like U gets assigned the value of something else, right? Literally what happens is whatever value is stored in T gets copied into U, right? So U gets the value of T. So U gets the value of T. So in other words, U also gets the value 700A. Right? And what does this mean? It means U and T both refer to the same list object here. Right? If you use T to change this object, right? So T add 1, right? And then you ask U how big is T, U will say, sorry, and you ask U how big is U, U will say it's now size 1. Right? If you ask for its first element, it'll tell you it's 1. Right? U equal T means they both refer to the same list. And this is exactly what happens in Python. Right? So if you make a list T in Python, right, and then you do U equals T, and then you write U0 equals 100, if you print out T, you get 100, 1, 2, right? And it's because Python uses references for all of its variables, right? In Java, the type array list is a reference type, so you get the same behavior. You had a question? Yeah. 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 Yes. Sorry, if you do what? It depends on what you do with T. So you have to be careful here. So if you modify the first element, yes, U changes. So if you write okay, so if we write T's new array list, U equals T, and then we write T dot add 100, right? Right, and then I ask you, how big is U? You get 1. Same size as T, right? Because U and T both refer to the same object, right? Here there's only one list. That's the key here, right? There's two variables, T and U. Right? So two variables, T and U, but they both refer to the same list, right? There's one object that holds the values of the list. This is Python, right? So in Python, oh, it's the same thing. Sorry, no, it's similar. So in Python, you have a list 0, 1, 2, right? You write U equals T, and then you write U0 equals 100. The value in T, the value in the original list changes to 100. Yeah, so if you ask T, what is your first value? It's 100, even though you changed it through U, right? Right? So here the key is there's one actual list object. It doesn't matter how you modify the object. If you have a reference to that object, they'll all see the same change. So the question is what happens if you write that? So now if I write T equals new array list, right, what ends up happening is somewhere else in memory, a new array list pops up. So if you make a new array list, a second array list object shows up in memory, and T now points at this array list. So if you, up there at address 101, T now becomes 800A, so T now refers to this list here, right? And now if you modify the list using T, U doesn't see the changes anymore, right? Because U refers to the original list. Question? Okay. All right, the object model. So when people talk about object-oriented programming, they're referring back to, they mean you're using a language that they're using a language that has some sort of model of an object. So what I'm talking about here is Java's model of an object. Not every object-oriented programming language has the same object model. Okay, so what did we teach you in 121? We told you you've got some variables, they hold data. We've got some functions. You can pass in data to the functions, and they can work on the data that you pass into the functions, right? So in 121, you did something called procedural programming. You broke your problem up into functions. Functions got data that were passed in via its arguments to operate on. So object-oriented programming focuses on something slightly different. Right? It takes a program and decomposes it into interacting objects. Every object has its own data and can operate on its own data. So there are four main elements to our object model. There's something called abstraction, there's something called encapsulation, there's something called modularity, and the fourth one, hierarchy, we'll talk about later in the course. Okay, so what do these terms actually mean? Okay, so there's this term abstraction. And this quote comes out of a book called Object-Oriented Analysis and Design with Applications. Right? And so the quote says, abstraction is one of the fundamental ways that we as humans deal with complexity. And abstraction denotes the essential characteristics of an object that distinguish it from all other kinds of objects and thus provide crisply defined conceptual boundaries relative to the perspective of the viewer. This quote doesn't tell you very much unless you already know what abstraction means. Right? And so the simplest way to think about what abstraction is, for the purposes of this course, is that you can look at a function or a method, right? And you can look at what the method says it does, right? So the string class has some method called toUpperCase, right? And you can use that method. You don't care how it actually works, right? And this is true of this is true in 121 as well, right? You can write a function somewhere, you look at the documentation of the function, right? And you can call the function without ever having to worry about how does the function actually do what it says it's doing. Can you stop talking, please? Thank you. All right, so, and so the idea here is that you don't worry about how a method or a function works, right? You simply need to know what it does, right? And so the same is true with classes, right? So you've got this string class, you have no idea, well, you probably have no idea how it's actually implemented, right? But you can still use it without any issues, right? In real life, you can drive a car, and I'm pretty sure almost no one in this room actually knows how a modern car works, right? You don't know how the steering works, you don't know how the gas pedal works, you don't know how the engine works, right? But you can still drive a car, right? And so that's the idea of abstraction, right? You have this model of an idea, right? You don't care about how the actual implementation details work, right? What is this relative to the perspective of the viewer? What does this mean, right? And so the idea here is that imagine you're writing a video game that involves racing cars. So you make a class called car to represent your cars. You then go on to another project where you're trying to sell cars in real life. So you're making like autotrader.ca, right? So you create a class called car, right? The two classes that you develop are going to be very different, right? One of them is for someone who's writing a video game, right? The other one is for someone who's trying to sell a car, right? your abstraction or your model of a car changes depending on what you're making this class for. Okay, encapsulation is often confused with or often includes something called information hiding. So this one's a bit confusing. So encapsulation is the process of compartmentalizing the elements of an abstraction that constitute its structure and behavior. Right? And so encapsulation, all it means is taking data and the operations that you can perform on the data and putting it into one place. Right? So this idea of data and operations, that sounds a lot like a type, right? And which we know are classes in Java, right? So classes are user-defined types. So classes are one of Java's mechanisms for encapsulation, right? We can put the information that an object requires and the methods that the object can perform on that information into one place, right? So we call that encapsulation. Many people say that encapsulation includes hiding the information from everybody else, right? So if an object has some information, you can only modify the information or access the information by asking the object, right? And so many people will include that as part of encapsulation. And so they'll say encapsulation is like taking your data and putting a capsule around it, right? So the capsule is impenetrable, right? Someone can't reach in and change the data themselves. Finally, there's modularity. So in 121, you broke up a program into individual functions, right? But there's many ways that you can break up a program. So this is all that modularity means, right? Modularity means decomposing your program into discrete components, right? And so Java has many mechanisms for modularity. The class is one of them, right? Inside a class, you've got methods, right? So which correspond to Python functions, right? And so that's yet another level of modularity in Java. There's something called a package that you've sort of seen on the assignments. That's another version of modularity. And there's something called a module in Java, which is yet another version of modularity in Java. All right, so that's plenty for today. We'll pick this up and start talking about how you organize a Java program in the next lecture.